we did a panel a few NANOGs ago, I can't remember how many, about basic traffic engineering and what people were doing on the network. And supposedly on various people's comments forums, they decided they wanted to see more. And in theory, my name came up, and I curse you all for it. So we're here back again with different people and a different setting. This presentation kind of changed midstream because at first we were going to do it as a traffic engineering working group out of the IETF, and we were going to present the framework document and what was going on in that working group to try and get some operational input. And midstream, we decided to have an interim meeting here, that's happening here on Wednesday. So we kind of shifted the focus because we didn't need to absorb a whole hour doing that if we were going to spend a good part of Wednesday. So it's split between what we're going to do on Wednesday and the framework document for those that can't make it, and talking to various people about what they're doing today in their networks. So I have Daniel, who's not MIA. Ooh, oh well, you can forget the MIA part because he made it like in the last minute. No, you can't hit your cell phone. Jim from Level 3. Brenda Freiberg from Intermedia, and BJ Gill, who's now with MFN. So first is going to be Daniel, and I'll let him talk and about the framework document and anything else he has on his list, and then we'll move on to some examples on how TE is in use today. Ready, Dan?
Okay. I'm just trying to get this booted up. My name is Daniel Audiche. I work for UUNet, and I co-chair the traffic engineering working group in the IETF with Ed Kern. So I'll give a high-level overview of some of the conceptual issues that are associated with traffic engineering. I'm not going to go into specifics. I'm sure some of the panel members will go into more specifics about their network architecture and how they deploy traffic engineering methods in their networks. While I wait for this to get booted, we're going to have an interim meeting of the traffic engineering working group here, not in this room, but in this hotel on Wednesday from 9 a.m. to 1 p.m. And in that meeting, we're going to review the framework document in great detail. And we're also going to discuss some of the new work items that Ed, Kern, and myself have come up with to try to focus the working group and to try to make some of the products to be more specific. We certainly welcome more input from network operators in some of the traffic engineering working group work items. It looks like this is taking its time trying to get booted up, so I really apologize for this. Up and running. Yeah, I think it's probably best for me to come in second while this gets booted up.
So we'll have Jim come up, who's going to give an example on what a fully deployed CU system is, right, Jim? What's that? Cool.
Okay, like Ed said, I'm Jim Boyle, level 3. I just want to kind of give an example of MPLS backbone architecture. Probably best to start with where we were coming from. Back in '98 was when we started offering services, and we deployed a ATM network over which we deployed a lot of different virtual networks across it. So we had routers that were dedicated to our internet service, routers dedicated to our internal and management networks, and routers that were dedicated to our voice product. And they all basically had their own independent PVC meshes across that. The reasons why we did that is because even though we're a facility network, it takes a long time to get all the fiber out there. So we were leasing capacity, and it allowed us to get one big pipe and put all of our traffic on it, and to some extent be wrong about where the traffic was going to be. It also isolates the different networks in terms of routing and QoS and things like that. And what do you know, it's pretty cost effective. The reason why we were moving away from ATM was because the capacity of our little ASX 1000s had long been exceeded. So we had to do something. The decision to go with packet over SONET was mostly because that's what's out there in the marketplace now. We still wanted to have a multi-service network. We still are leasing in a large portion of our network. So it does make it very effective to have all your capacity basically in one basket. We wanted to be able to support a customer VPN product, which to some extent indicated that we would need a virtual network approach or end-to-end MPLS, and using things like RFC 2547 or however those numbers go together. We wanted a scalable design, of course, something that's more manageable or easy to manage than an ATM mesh network. As a lot of people here are probably familiar with, one of the problems with ATM mesh networks is got a lot of ATM PVCs you got to keep track of. And when you add a new network, you have a big task ahead of you in terms of touching every other router in the network. And also we wanted to make effective use of complex topologies. What we came up with was that we had already came up with a hierarchy, a transmission hierarchy between our different gateways. Some gateway connections were at higher capacity than others, and we continued that by making those become the highest capacity packet over SONET links, and that's where we do our traffic engineering. We use a full RSVP traffic engineered mesh to interconnect all the routers, and then we are planning on using LDP to pull in MPLS traffic from within the gateway and also from smaller cities. We also use, kind of, I guess, a side note, backup LSPs to speed up convergence around failures in the network. And like I said, it's currently only an IP network with a RSVP traffic engineered subset. Probably, and that's where almost all the traffic is also. And we are working on an LDP rollout over the next couple months. How those will interact is, let's see if this works, is in this area where the red blob is, LDP will be used to pull in traffic from the gateways or from sites like St. Louis, Cincinnati, et cetera. And then in the middle here, we use an RSVP mesh and then LDP also in order to get traffic into the core, across the core in a capacity-constrained, CSPF manner, and then out to the appropriate egress MPLS edge router. And so the purple lines here are basically our high-capacity OC48 type links, and the blue lines are either legacy or basically smaller capacity ATM links that we'll hold on to until we either get there with our own fiber or the capacity warrants an upgrade to that site. We would use LDP to pull in traffic, for instance, from Houston into Dallas, or from the routers within Dallas into the wide area network routers. And just in case you're wondering how the signaling all plays together, the fact that we're using LDP here to pull in traffic, in this particular diagram, A through E correspond to our RSVP traffic engineered core. X and Z are MPLS edge routers attached to them. The fact that we use LDP to pull traffic in here, and also to get traffic out of the network, requires that you have to run LDP basically in conjunction with your RSVP LSPs. And so in this particular case, I'm sure I'll have the slides available, but for later perusal, but A is told X via LDP a label to use. And because of the SPF shortcuts that are used, A knows that to get to Z, it has to go through C, and that it has an LSP associated with that. It runs a directed LDP session to get a label that C is requesting it use within that LSP to get the traffic out to Z. And so that's basically how it all works together. I'm sure there'll be questions on that one. But that definitely is I believe, a unique approach on how to use the protocols together. Is that it?
So from an example where the majority, or I guess all of the background traffic is actually going across?
Because you have to go across more or less one of those links to get to a pairing point, I would probably characterize it as 80 to 85% of the traffic goes over an LSP.
So I wanted to have a different example of someone who, while it's fully deployed, doesn't actually use it all the time or even for the majority of traffic.
Hi, I'm Brenda Freibar from Intermediate Business Internet, and I'm going to talk about our experiences using MPLS. Like Ed said, we don't use it as much as they do on a wide scale on our backbone. We use it basically as we need to make up for the lack of flexibility that the IGP doesn't provide. We've been running it on our network for about a year, and it was implemented because ISIS was not sufficient enough to meet all of our needs. Basically, it just allows us to control traffic flows and alleviate congestion in busy areas. That's mostly what we use it for. Like I said, we use it as a last resort as opposed to a primary means of traffic engineering. Basically, it does allow explicitly routed paths, so excuse me, it allows routes other than the shortest path to be used. So the way we use it to alleviate congestion on a path that has the lowest cost, multiple MPLS tunnels are built from a source to a destination so that it load shares over multiple paths, multiple unequal paths. Basically, when we deployed it, we experienced a few problems. Basically, being a new technology, we came across a number of bugs from the range of certain MTU bugs to problems with our OC48 line cards. We've also found that using it on a limited basis that we do, it scales fairly poorly because we have to manually configure tunnels whenever the need arises, and we have to keep track of where all those tunnels are and provide external documentation. Like I said, being that we only use them when necessary to make up for the insufficient granularity of ISIS, we have to keep track of where they are, which makes it more complex to troubleshoot routing problems and yeah. Basically, what constraint-based MPLS should do for us but doesn't, theoretically you shouldn't have to specify the amount of traffic expected to flow between various points in the network. It should automatically analyze traffic flow, calculate the best paths to carry the traffic, and establish explicit paths as the result. That's what we'd like it to do. And dynamic LSP generation and mapping the traffic into tunnels would reduce the need for manual configuration and make it more scalable on our network. Basically, we are planning on broadening the scope of use of MPLS on our network. We're looking into doing ATM over IP using MPLS and also MPLS VPNs for customers, as well as class of service type things. And that's about it.
Ready, Daniel? Back to Daniel.
Hi, once again, my name is Daniel Audiche. I work for UUNet. I'll give a very high-level overview of some of the conceptual issues associated with traffic engineering in IP networks. So what is Internet traffic engineering? Basically, it deals with the performance optimization of operational networks. I'll talk a little bit about what I mean by optimization in some other slides. It is an application of technology and scientific principles to traffic measurement, modeling and characterization of traffic attributes and network parameters, as well as traffic and network control. So TE is not really specific to any particular technology. You basically try to make use of the most appropriate technology at any point in time. So TE can be accomplished in many different ways. The method that you choose will probably depend on the kind of business model that you have, on the kind of technologies that are available, as well as the kind of insights that you have into some of the fundamental problems. Traffic engineering will evolve over time as technology evolves and as we get better understanding of some of the fundamental issues. So what is optimization in the traffic engineering context? It clearly is not a one-time goal. It is a process, an iterative and continual process of network performance improvement. It's fundamentally a control problem. And the basic problem is really, you have capacity and you have the demand. And the basic issue is to map the demand onto the capacity in the most effective way to deliver the highest level of service to your customers. Traffic engineering is a very complicated problem if you want to do it very well. And some of these complications arise from two basic aspects. One is that the IP traffic or the IP network optimization problem operates over multiple time scales. And also you have various granularities of traffic resource allocation. So from a time scale perspective, you have long time scale kind of issues, aspects that relate to capacity planning for the network, as well as control over the routing infrastructure, which is basically an intermediate time scale control problem. You also have very, very short time scale control issues, which pertain essentially to scheduling and queue management, basically to service policy within each particular network element. So essentially, you have the concept of traffic engineering in the large, where you're really trying to optimize a very large-scale network over various time scales. And that's what we call macro traffic engineering. You also have traffic engineering in the small, where you're basically dealing with the high-resolution dynamic aspects of the traffic, which basically localizes the problem to specific network elements. So how does traffic engineering relate to business? Because obviously technology is only useful when it actually serves a particular business need. And it turns out that traffic engineering is fundamental to the service provider business model. And what are some of the needs of service providers? Well, you want to leverage your assets to deliver competitive and hopefully cost-effective service to your customers. You want to increase service quality while minimizing costs. Again, this goes back to trying to leverage your assets as effectively as possible. You want to be very responsive to the needs of your customers, which evolve over time. Therefore, your network really needs to be agile such that you can reconfigure it and you can develop new business models as the service demands from the network evolve. You also want to have a scalable and extensible network structures. And perhaps most importantly to a lot of people here, you want to automate as many of the operational processes as possible so that you minimize the amount of human intervention that is involved in network operations, and thereby you minimize the amount of human errors, and you also improve the effectiveness of your network with respect to delivery of service to your customers. So what are some of the control technologies with respect to routing? The classical approach is obviously the IGP approach, whereby you adjust your link metrics in order to try to map the traffic onto your topology in various ways. Primarily, you're trying to minimize congestion, minimize packet loss, maximize throughput through your network, and of course minimize latency too. It turns out that the conventional technique has a number of problems, and I have a lot of published works that elaborate on some of these problems. Although there's some debate as to whether these techniques are really as ineffective as they're supposed to be, and I'll be happy to debate on those aspects if anybody wishes to do so. Then we have the classical overlay models, primarily based on IP over ATM or IP over frame relay. And the basic premise is you basically introduce a technology that has virtual circuit capability within the core of your network. And you use the virtual circuit to control the mapping of traffic onto the infrastructure. And then you use your IGP metrics to adjust the selection of virtual paths. This gives a number of advantages, one of which is that you can actually measure traffic on the virtual circuits. And by so doing, you can get an estimate of your traffic metrics within relevant parts of your network. And this is a very crucial advantage because this turns out to be very useful for both optimization as well as for long-range planning. The other approach that is now being kind of pushed forward is the MPLS approach, which almost everybody knows. The two previous speakers have talked about the applications. But basically, MPLS can operate in both an integrated kind of mode as well as an overlay mode. There's a new concept called the forwarding adjacency, which essentially allows you to advertise LSPs based on configuration. So you can basically mimic the IP over ATM model if you like that approach, or you can have an integrated approach where you basically establish LSPs and map traffic onto them without an explicit overlay. And then we have the new concept of multi-protocol lambda switching, which basically will exploit advances in optical networking technologies. And this is going to have a very, very fundamental impact on how we do traffic engineering. And actually, John McQuillan wrote a very nice article a couple of days ago on some of these aspects with regard to some of the fundamental ramifications on routing. So there are many subtle merits to applying traffic engineering systematically in your network. One of the merits is that it allows you to structure your goals and priorities with respect to improving the performance of your network, hopefully in a very systematic and methodological kind of way. And it also allows you to measure and assess the effectiveness of these goals, as well as the policies that you implement. So here are some policy concepts for traffic engineering. Basically, you can have policies that are predictive, where you really try to predict what's going to occur in the network, and then you take preventive action to try to obviate those undesirable states before they actually manifest in your network. Clearly, this is a much better approach than the reactive approach, where you are trying to respond to events that are already occurring in the network. But perhaps the best approach is the perfective approach, where you seek to improve your network performance even when no problems appear to be evident. For example, at UUNet, we are deploying OC192 network infrastructure right now, even though we could possibly do with an OC48 and trying to apply a bunch of control actions. So that's an example of a perfective kind of approach to traffic engineering. But it turns out that you actually need to apply these three approaches concurrently in your network. So what are some of the issues in traffic engineering? Well, one of the issues that I've noticed in my own context is that there is a need to reduce the intellectual gap between the concepts and the practice, right? Which means that there needs to be collaboration between people that are trying to introduce this concept as well as people that are actually going to use these concepts to run the network. There needs to be better measurement systems in IP networks, and there's a need to automate a lot of the process models. There's also a very, very strong need for tools and support systems for traffic engineering. We also need to gain a better understanding of the dynamics of IP traffic. Okay, here's a very interesting paradox. And this paradox is actually well known in road traffic engineering. And it shows that under some conditions, adding capacity to your network can actually degrade performance, especially if you're not conversant with some of the traffic engineering issues. So in this diagram, I basically have two parallel paths between two nodes, A and F, and traffic from A to F is split between these two nodes using, for example, ECMP. Let's suppose that all the links are equal costs. Now let's suppose that we add a new link from G to C, right? And let's suppose that this link actually has much higher capacity than the rest of the links in the network. So you will associate either the same or a lower metric to this link. Now what happens? You lose the equal costs parallel paths that you had before. Therefore, you're going to get congestion in C, in D, because all the traffic from A will now have to pass through the A to D link, which is a very low bandwidth link. So adding capacity without understanding the traffic engineering issues can indeed degrade your network performance. And if you have questions, let me know. We can discuss some of the framework issues on Wednesday at the IETF interim meeting.
Okay. So I have my set of questions. If people have questions, they're welcome to pop up to the mics and we can throw them in line. My first one, and we'll start down here, is when you originally deployed, what was the problem set that you were after it fixed? Why did you think about going to the trouble to try and deploy a ATU system? The ATM network? Sure.
Yes, basically the problem we had was that in a very large, dense, this is when I'm wearing my UUNet hat, even though I no longer work for them. The problem was in a very large, dense network like UUNet, due to the huge amounts of traffic we had internally, it was basically impossible to calculate out in any reasonable time frame what to set the global metrics to before adding new capacity. This would result in all kinds of issues, congestion, as Daniel demonstrated with that slide up there. Not to mention the human cost when there were link outages. The UUNet network is so large at this point that at any given time we have how many OC48s down? We have, at any given time you have 2 or 3 OC48s down within the network, which is a non-trivial amount of traffic. So most of our TAC people, Blaine, Rick Glaser here, we're sitting around working metrics up and down trying to figure out what the optimal paths were. So at that point we decided instead of putting it all on the humans, we should try and automate it as much as we possibly can and put in PVC contracts and ATM networks, which at that point were traffic engineered using PNNI spans for forethought. Yes, and then so basically what involved was we had a set of full meshes per region and a transit region which is also a full mesh. This obviated the n-squared meshing problem because we did not have edge-to-edge meshes. And then basically we sat on our 4 switches and did PVC contracts by measuring traffic flow from edge to edge. Since our network was large enough that they were the superflows, hub-to-hub superflows were tractable to analysis. So basically we had a formula which every week Aaron France and Jim Freely used to run, which multiplied the capacity by 1.2 and reset the new contracts. Boom, everything else sort of just worked after that, barring specific pathologies which Blaine and company are supposed to fix.
Well, as far as intermedia goes, like I said earlier, since ISIS prefers basically the shortest path, we had lots of overutilized links and lots of underutilized links. So basically we set up MPLS to basically divert some traffic and route around those overutilized ones. And
was it just backbone links or was it also 2 peers?
Both, a little bit both.
So basically you were routing around congestion.
Yeah, right around congestion, that's the primary reason why we use it.
The question is, what are the...
What was the problem set? What were you trying to fix? What couldn't you do with that fix?
Probably the biggest thing is that we needed some form of MPLS to allow us to do VPNs across the core. So that was probably the biggest driver towards MPLS. Basically taking our traffic projections and putting them out towards likely topologies, we also knew that we were going to come across some awkward topologies, both in steady state and also during failure. And so going with the traffic engineered core, while we could probably do without it, you could probably make an argument that you could go without it. Probably a couple months after you got rid of it, you would be wishing you had it.
Dan, do you have anything to add? You want to add anything?
Well, I think most of the stuff has already been talked about with respect to Unet, but I just want to add that our network is characterized by a number of aspects. One, as has been noted, it's a very, very large-scale network with very, very complex and dense topology. Secondly, the traffic is evolving very, very quickly, much, much faster than the topology is evolving. Therefore, you need a very, very agile and flexible mechanism to be able to map the traffic onto the topology. And these are some of the primary motivations. There are some aspects of using only ISIS or OSPF metrics that people have not really talked about. One aspect is the impact on BGP. For example, if you globally change your metrics periodically, that's going to change, especially if you use shortest exit policy, which is what most people use. That's going to change your exit, your BGP exit selection, and that will in fact change your traffic metrics, right, which makes your original calculation invalid. And this will also impact the traffic metrics of other service providers. So you're going to get traffic shifts all over the internet. If a major provider like UNet starts doing global arbitrary metric changes over its network. So these are some of the aspects, in addition to the advantages that have been mentioned before, that one needs to consider.
Okay. Name and affiliation when you come to the mic.
It's John Coulter, Cisco Systems. I had a question, actually two questions for Brenda. You had a comment on issues with TE scalability. I was wondering what would be your, what's your impression, or do you think you could provide the same type of function using another method, using traffic engineering through layer 2?
Well, basically, I think for what we're trying to use it for, it works just fine, but we do want to use it on a wider scale, so, and we found that we really haven't been able to implement that very well yet. What exactly, I don't know if that answered your question quite.
I was wondering if you think that you could, if you would not have the same scalability issues trying to do the same things with other methods, and how you would, or what you would need, or where the scalability issues come. Is it in the operation of the network? Would better tools help deal with that?
Well, basically the scalability issue comes into play because we have to manually configure tunnels to fix random things. And basically, if we had like a type of dynamic LSP generation where we wouldn't have to configure everything, that would make things far more scalable.
So a more intelligent routing protocol.
Exactly.
And better tools. Actually, one other question, you said you were looking at deploying ATM over IP. I was wondering what type of traffic you would expect to be running. What type of ATM traffic? Would it be IP over ATM or some other native ATM application?
Actually, I'm not part of the group that's really been working on that, so I really don't have a good answer to that question.
Just take offline.
Yeah.
Thanks.
This is Sanjay Agrawal from Luminous Networks. I have a question for Jim Boyle from Level3. You said you showed a core network, and in your core network, you said that you have MPLS in a core, and you have fast readout paths. Essentially, you have alternate LSPs in case some LSPs fail. But looking at the network, there are very few nodes you showed. And at that routing hierarchy, usually there are very few nodes in any network. So a single node failure can bring many LSPs down. How do you ensure, first of all, that your alternate LSPs are spatially diverse enough that when the primary LSP fails, alternate takes over? Also, my actually reservation about this is that many LSPs may fail, and if you look at many of the service level agreements, customers want availability over anything else. And in your network, if you were to use traditional routing protocols, then there are many, even if one node fails, many alternate paths still exist, which your MPLS will not be able to utilize. So that's the reason why I always have tried to make an argument about differentiated services, which uses traditional routing protocols, as opposed to MPLS, which has a problem as far as, I think, robustness is concerned. So as far as traffic engineering and QoS is concerned, both of them address it, because that is a matter of controlling traffic loads relative to the network capacities. So comment on that.
Sure. Is it still on? Okay. One of the things that we worry about most is not so much nodal failures as much as link failures. And what we basically do is we just tell the routers, hey, set up a secondary LSP in association with this one right here. And they know where their primary LSP lies and basically can establish an independent secondary LSP. In an ATM network, you can do very similar things, especially with that type of topology where, not the backup type SPVCs, but if you get a failure, you get a signaling storm, everything comes to, for instance, on Chicago to New York City in that topology, everything flows through Dallas, so as long as Dallas can stay on top of the signaling load, it's fine. And the twist here is basically that your backup LSP is pre-established. So all you have to do is signal to the ingress node that there's a failure along the primary, and it just has to switch the routes to the secondary. So there's not a lot of manual process involved there, and you do have to make sure that you don't, for instance, have primary LSPs that do share a facility with secondaries unbeknownst to themselves and things like that. So,
okay, so
there's some tricks to approach that as well.
In your experience, it has been the links which fail more often rather than the routers. From what I have personally heard from talking to several people, it was the routers which fail more than links, but I guess...
Well, I deleted all the pages on my pagers, but I mean, every time I get pages because this OC48 or that OC48 is going down more so than this router's dived or that router's dived, so, yeah.
Sean Dowland, Equinix. My apologies, but I want to throw out a few marketing buzzwords that usually get used with this. One question, has anyone successfully used MPLS to defer bandwidth upgrades to their network? And secondly, has anyone used MPLS to do QoS to their end customers?
Well, basically, not specifically MPLS, but traffic engineering in general has been used to not necessarily defer upgrades, but to ensure that the existing capacity that we have is utilized more optimally while we're waiting for more. It's not, I mean, at WorldCom we had enough capacity coming online that it wasn't really a big deal. It's just depending on when they could engineer their OC192 circuits up. Our traffic flows in our model were fairly tractable, so we had fairly good projections. In fact, I used to work with WorldCom on engineering capacity because we knew what capacity constraints were going to be better than most people due to our architecture. So as for quality of service, currently at GE and when I left, this was still under debate. Daniel would be able to speak to that more.
Right now, MPLS has not really been widely deployed, and the issues that relate to mapping MPLS to scheduling and queue management kind of functions, in other words, the relationship between MPLS and vServe is still essentially being built within the IETF. But MPLS and similar techniques do indeed allow you to improve the quality of service to all your customers.
And I would say that if your capacity, if you assume your capacity doubles every 3 or 4 months or whatever the case is, you're really not deferring a capacity augment as much as you are getting around a tough spot when, for instance, a field tech decides that he needs to redo an OSP panel or something like that. I mean, you've ordered the capacity, you're sitting there waiting, and you're burning your network. It allows you to get through those type of tough spots, really, more than deferring capacity augments.
And moreover, given that the traffic is increasing exponentially, you can't really afford to defer capacity increments. But being able to know your traffic flow characteristics will help you to deploy the capacity in the best way, and will also allow you to make more effective use of that capacity once you've deployed it.
Yeah, hi, Ted Seeley from Sprint. This is a question kind of for Daniel and VJ. Daniel, you had in your slide multi-protocol lambda switching going forward, and I'm curious what you're implying there, whether you're implying that you're using nailed-up wavelengths in your network like MPLS tunnels, or that you've got wavelength switches that are doing protocol interpretation and routing, which is not something we can do today or for a long time. So I'm curious what you're talking about there.
First of all, we have to define what long time actually means. But multi-protocol lambda switching essentially is a technique that we proposed, and it's a very active area within the IETF right now. The basic premise is that you can apply some of the control concepts that has been developed for MPLS traffic engineering in the optical domain. Moreover, given that there's a new class of optical switching elements that are programmable, reconfigurable, and very versatile, you can basically establish optical channels very, very quickly in close to real time. And if you can accomplish this kind of objective, this means that you can match your capacity to your demand in a more effective way. In other words, your topology becomes more agile. And this has very, very fundamental implications. John McQuillan wrote an article a couple of days ago that explores some of the implications of this technology on routing. But this is still under development, and it will take a while for it to come to the market.
So what you're implying is then just...
Well, at Supercom, there were a couple of companies, I mean, I can't mention company names, but there were a bunch of companies that demonstrated products based on this multi-protocol lambda switching concept.
So these are just nailed up wavelengths in your network based on some sort of event or trigger that happened in the network, but you're not doing any sort of protocol routing at the wavelength level.
Okay, basically, you need to be able to establish wavelengths very, very quickly and automatically. You need mechanisms for resource discovery.
So that's just fast reroute at the wavelength level.
Yeah, okay, so you need the routing kind of control functions to be able to discover resources and to be able to disseminate topology state information. Then, given this information, you need to be able to compute optical paths through the network. And then you need a signaling mechanism to actually instantiate those paths using, for example, RSVP or CRLVP.
All right, one more question. How soon do you anticipate UNet being able to actually implement such a model?
That's not within my province of authority.
Okay, thanks, Daniel.
Last question.
Stephen Wright, South. Question for Jim Borrow. Given the difficulty that Brenda had reported with scaling these tactical LSPs, could you talk a bit about the control problem that you have with your network? And in particular, could you give us an idea about the scale in terms of the number of LSPs or the number of labels you have, and what sort of percentage of those are manually configured versus automatically generated somehow?
Yeah, that was something I was thinking about when I was listening to Brenda talk. I think one potential difference is that, like I said, we're coming out of a full mesh ATM network, so we've got a lot of configuration systems that are used to doing things like generating these type of configurations, and so we have a lot more automated configuration control, I guess, and that's probably another reason why we've got a full mesh of LSPs between our wide area network routers, because it's probably more easy to do that than to decide which LSPs to deploy. And in terms of scale, I guess we have like 10 or 11 gateways up there. Each of them have 2 WAN routers, and they're fully meshed, so whatever that comes out to, a couple hundred or so.
Let me try and ask it again. Brenda's use of LSPs was primarily for routes that were not shortest path. How many of your LSPs do not go on shortest path routes?
None of them.
Okay, just the last few things. Any other questions before I babble? Okay. So, I couldn't moderate without spouting some, so this is the me spouting part. Not with the Digix hat on, not with the working group hat on, and no, they're not going to be slides online that can be held against me later. A lot of talk has been happening about using MPLS, and so a few things I wanted to cover from my personal opinion. This is not the simple way to do it. If you don't have to, don't go out of your way to deploy MPLS just because other people are doing it, or just because you think it's cool, or just because you have more work to do. It's just simply not necessary in probably 90% of networks. It's probably more expensive from an operational point of view than just buying the fiber in the first place. The reason you do it more or less is because you're waiting for install intervals, or you're waiting for pairing circuits, or you're waiting for this or that, where money can't buy you out of the hole. This is job insecurity more than job security, because it is a much more, you're adding complexity over a system. So be prepared for a lot more midnight phone calls. And it's also life insecurity, because you have a lot more people that want to do ill things to you. The good news is the vendors love it for the most part. The bad news is they want to put it on your network whether you like it or not for the most part. Do you need this particular hammer that they're coming up with? Well, you can do lots of neat accounting tricks with it. Certainly one of the things I first used it for. You can break down numbers and segregate as far as how much any specific path, any specific route, anywhere, how much bandwidth is it taking up, just by changing a forwarding path or adding a new LSP. The biggest issue is once you have all this accounting information, are you really prepared to look at it and do anything with it? Congestion is the biggest one, of course. If you have hot shortest lengths, or you have an overloaded closest exit peer, or just simply have a large number of diverse paths you need to bond together, this might be the way to do it. Fast failure rerouting is what some people say. There's many different ways to do fast failure rerouting, so I wouldn't hold that up anymore as a good reason to deploy MPLS. Executives and the big picture people hate clouds. They hate being that ambiguous. They love a fully nailed up, this is where all the paths go, this is how much traffic they can carry. They love it to pieces, so that might be a force down. And for some people, just carrying IP traffic isn't enough. Don't know why, but convince them that a separate network still might be the better way to go. If you really feel the need to punish yourself, there are better things to punish yourself with, like multicast. IPv6, and just ignore that last one, or the person affiliated with the last one. And as I stand up here, I've come up here before, and I'm supposed to be the one that loves it. And I still think it serves a purpose, but it serves a purpose in about 10% or less of networks. But we do need to document why people need it and why they're using it, so we can give the vendors and various people an understanding on what needs to get built into the system. Always remember the vendor's goal. No. I figured just one hidden thing in there is enough. Okay, putting my co-chair hat back on. If you end up, deploying a system, Daniel and I want to know about it. And it was basically the same questions I asked the folks up here. What's the problem set you're trying to fix? What type of, and scope did you deploy the system? The problems you had during the deployment? Looking back after you do it, was it worth the trouble of deploying it? The overall upkeep of the system, is it easier or harder to maintain operationally? And would you do it again looking back? And the most important slide, please fill out those comment forms. Please fill out those comment forms. Just ignore that crazy person sitting over there. Thanks. That's it. Have a good lunch. Thanks to the speakers, including DJ.
All right, this is just one question. I keep hearing that traffic engineering has a very high operational cost. So I thought we might ask the people who are operating the largest network in the world with traffic engineering what their comments are. Blaine? Yeah.
And to be specific, it's operational cost for the 90%. For the 10%, there might not be a better way to do it.
Right.
So,
Understood. Blaine UNet for everybody. I guess the question I have for you is if you plan on not implementing MPLS at OC48 and OC192 speed, what are you going to do with a sparsely connected high-speed network? What are you going to implement are you going to just manage all your IGP metrics offhand? You're going to use something like Wandle and try and be very deterministic? How are you going to know when you have link failures that your traffic is going the next best path, especially if it's a very large, sparsely connected network?
I think instead of sparsely connected, what Blaine was trying to say is well-connected, densely connected partial mesh.
There, okay.
a densely connected partial mesh.
And one question I'd have for the UNet operations would be how much of your time is focused around problems revolving around MPLS as opposed to circuit failures, hardware failures, et cetera?
We don't spend a lot of time with MPLS problems. We just don't have that many.
I mean, basically the problem
So many other problems.
It's not, actually MPLS it's not quite at the point where we want it yet. We're working very hard on getting it to that point, and Daniel's alluded to some of that. And when it reaches that point, it will be pretty much similar to the way that we're going to deal with, or that we deal with the current ATM network.
Basically, the current ATM traffic engineering methodology consists of a set of scripts that run every week. Aaron France used to spend about an hour every Friday updating the contracts, then they pushed it out. So basically, total man time, once the bugs were worked out, this is true of any other technology as well, was about 2 hours man time, and it ran UNet, which I think is a pretty good statement on operational cost.
I'm not even necessarily saying that MPLS isn't the end goal. I'm saying, do you need it right now? And, you know, what is the percentage of networks that truly need it and why? And quite frankly, from my point of view, sitting on a non-UNet network, if I don't particularly need it right this instant, I'd much rather take great pleasure watching you throw yourself on the cross first.
I'll admit that a lot of people probably don't need this, but in a network like ours, we do need something like this, so.
Yeah, and I'm not, once again, we go back to the 90-10 or what that percentage is. And for those people that do need it, we're interested in knowing why and what's missing, but I know you know that.
So just out of curiosity, you're saying that you don't need it right now, but you are saying that you need something like MPLS, right? Because otherwise, what are you going to do? Are you going to do all DWDM and have everything that you need, or?
I've deployed it, I've used it, and found it practical for what I was doing it. Yes, you know, some other system, you know, DWDM based, you know,
Yeah.
don't know. It's just don't want to forgo a better way of doing things just by, you know, swallowing, you know, the MPLS pill and having happy hallucinations.
Yeah, I think the bottom line here is that different networks have different structures, different business models, and different operational problems, and therefore you should really deploy what you consider to be the best for your network at any point in time. All these technologies will evolve over time. So after MPLS, you're going to get multi-protocol lambda switching, and after that, you're going to get a whole bunch of other acronyms.
I have some comment on NPR systems for traffic engineering. My name is Xipeng Xiu. I'm from Global Crossing. Global Crossing probably has one of the largest NPR systems for traffic engineering in the whole world. We have thousands of tunnels in our network. From our perspective, the reason we need traffic engineering is that, first of all, we do all the fibers, but it takes some time before we actually get the fiber. And so during this transition period, we really need something to fix the congestion in the network, because the network is so big and so complex that tuning the IGP matrix or BGP attribute has become so complex, and it tends to have a global effect. That if you use MPLS, you can precisely control the distribution of traffic in your network, that it buys you the time until you get the traffic. So from our perspective, it's really useful. It does cause us lots of problems, but it also solves us lots of.
Right, and I think I put that in my slides that it can be quite effective, and we've used it as quite effective. I have in the past used it as a good stopgap approach, waiting for those delivery intervals. But that's not the same as passing the majority of the traffic as, you know, Jim's doing it, you know, 100% of the time. It can just be used as a stopgap. You don't, I mean, I guess I'm saying you can, you know, swallow 10% of the pill and not eat the whole thing. Oh.
You can't just go with, I've got my network, you know, that I've got in the state. You have to go with, I'm going to lose my limiting time. I've got to find next step.
Yep. No, he's commenting that you have to deal with failure. I didn't ask him to go to the mic because of time. I'll find. You can corral him afterwards like I'm going to do. Anyone else? Going. All right, now have a good lunch.